All right, good morning, everybody. My name is Mr. Dara. For those of you that don't know me, teaching physics here. We're starting in chapter 3. This is about acceleration. Just a few reminders here. First of all, the technical readings due date is coming up, and that extra credit deadline is tomorrow night at 11:59 p.m. If you don't meet the extra credit deadline, that's fine. The technical reading itself is due on the 23rd at 11:59 in the evening. So you want to make sure that you read through that information sheet, you meet those requirements. I'm looking for a minimum of 2.5 pages of information. You can certainly exceed that. In fact, you're encouraged to exceed that. But the absolute minimum is 2.5 pages. Please cite your sources, APA or MLA format. Whatever your preference is fine with me. Weekly extended response question number 6 is due tomorrow at 11:59 p.m. And just so that you're aware, because the technical reading is due next week, there is no weekly extended response question that will be posted for next week. And if at any point you have questions, feel free to email me, and I'll be glad to assist you with those questions. Okay, so we're starting chapter 3. This is about, again, it's called accelerated motion. The first thing we're going to look at here is acceleration itself. What is acceleration? It's simply defined as the rate of change of speed or velocity with respect to time. There's also average acceleration and instantaneous acceleration. Average acceleration, it is the change in velocity during some measurable time interval divided by that time interval. Now, we'll be using this idea of average acceleration as we proceed through the chapter. There's another type of acceleration called instantaneous acceleration. It is the change in velocity at an instant of time. So, for example, if you would happen to, let's say your video, you have your phone out and you're recording somebody driving down 21st Street and they are accelerating. Well, any instant in time that you capture that, let's say you take a video, then you also decide to take a picture of that. That picture captures instantaneous acceleration because it's that change in velocity at that particular instant in time. So just a couple of definitions there. I just want you to be aware of instantaneous acceleration. Just know that it's out there. Average acceleration, again, we're going to focus a lot on that as we, again, proceed through the chapter. Okay, so what we're going to do here is take a look at 2 different formulas. The first formula focuses on linear acceleration. Now, what I'll do here is I'll write the formula down. And I'm going to go through here and define the variables for you. Now, on worksheets, if you take the time and read the feedback that I provide in Google Classroom, for some of you, you tend to write down, well, acceleration is, you write down the rate of change of velocity with respect to time. When I ask you to define variables, all you really need to do is say, you write down this formula, or type in the formula on the paper, in the Google Classroom, and you say A equals linear acceleration. This is called V sub f. The f is a subscript. The reason why we're using subscripts here is because we have 2 different speed values and we need to distinguish between the 2. So V, you say it, V sub f. V sub f is final speed. It could also be final velocity. I guess really it should be velocity. So we'll fix that. I is initial, I-N-I-T-I-A-L, velocity. and then t is time. Time is going to be measured in seconds. A lot of times these problems will either have miles per hour or they'll be measured in meters per second. Please listen carefully to this. Whatever the units are that I provide, either meters per second or miles per hour, don't try to convert back and forth. It's a complicated process, and it's really not necessary for the scope of high school level physics. So just leave the units as they are. Do not try to convert. All right, so there's linear acceleration. So we'll take a look at some example problems here, a couple of example problems, and then we'll move on to angular acceleration. All right, so let's say that at first let's say you know the final speed, let's say it's 50 miles per hour, and that's after you increase your speed up from, I don't know, 30 miles per hour. And you're doing that in a time of, let's say, 5 seconds. This is going to come out to be a nice whole number here. So you subtract the final speed minus the initial speed, get that difference, and then divide it by the time. So 20 divided by 5 is equal to 4. Your units here are miles per hour per second squared. If you don't have the right units as part of your response, that's okay. All right, I'm more interested in you making sure that you understand the process and how you get to the answer. That being said, remember, always, always, always show work. All right, I always need you to show work because I need to see that you know how you get that answer. And if you just give me the answer without anything there, as far as I know, you might have guessed. I don't know. Okay, so we're saying that we start at 30 miles per hour, we increase our speed to 50 miles an hour in a time of 5 seconds. So your speed is increasing 4 miles per hour every second over a 5-second period. All right, that's what your answer means. If you had to explain it to someone who knows nothing about acceleration, you say, yeah, my speed increased by 4 miles per hour every second for a time of 5 seconds. Now, you can also have situations where you're obviously slowing down. So in that case, here's another example. I'll use a different color marker. In that case, let's say we're talking about you were initially flying down Route 16. Let's say you're going 65 miles per hour right at Newark, which you shouldn't do, by the way. And then you slow down. You have to slow down quickly because let's say somebody's watching you, and you drop that speed down to 45 miles per hour really quick in a time of, I don't know, let's say 6 seconds. Now, here's the thing. You're not always going to get a nice whole number like we did up here. Sometimes you get decimals, that's okay, it's not a big deal. So you still go ahead and subtract. It's always final minus initial, and then divided by the time. 45 minus 65 is negative 20. Negative 20 divided by 6, I don't know that off the top of my head, so there's where a calculator comes in handy for us. Negative 20 divided by 6 is negative 3.33 or so miles per hour per second squared. So your speed is decreasing by 3 miles per hour per second over a time of 6 seconds as your speed drops from 65 down to 45. Now, in some cases, we may have examples of extreme acceleration. If any of you have ever experienced top thrill dragster at Cedar Point, you know what I'm talking about. Personally, I have not experienced it, and I will not experience that. That's not me. But top thrill dragster, I believe the speed, I believe it goes from 0 up to 120 miles per hour in 4 seconds. You think about how incredibly fast that is. You wait 3 hours in line, then the ride's like 15 seconds long or whatever it is. But for some people it's a major thrill, but you won't see me on that ride, just throwing that out there for you right here, right now. Okay, so I'll show you that, an example of that, because sometimes the problem might say that you're starting from rest. And when you're starting from rest, your initial speed is 0, of course, because you're not going anywhere. So you've got 120, goes up to 120 miles per hour from 0 in a time of, I think it's 4 seconds. Let's say it's 4 seconds. All right, so you solve this, 120 minus 0 divided by 4. So that ends up being 30 miles per hour per second squared. Now, I'm pretty sure they don't have this on the ride, but let's say they did. Let's say that while it's taking off, you have this, let's say you have a speedometer in front of you. At 0, of course you're at rest. After 1 second, 1 second after takeoff, you're already going 30 miles an hour, so the needle's right here. 2 seconds later, after takeoff, your speed is doubled and you're up to 60. 3 seconds, you're up to 90, and 4 seconds, you're over here at 120 miles per hour. All right, in only 4 seconds. If you just count 1 1,000, 2 1,000, 3 1,000, 4 1,000. That was pretty quick. 4 seconds is very quick. And to go that fast in that short amount of time, well, let's just say that there's some G-forces involved. All right, but there'd be an extreme example of acceleration, something like this, or if you talk about drag racing, if you watch, if you're into that at all, you go from 0 up to, I think it's like 300 miles per hour in a short amount of time. So the moral of the story here is that acceleration is applied in daily life. All right, you've experienced it thus far. If you drive a car, if you've ridden in a car, whatever, truck, whatever, you're still experiencing acceleration. All right, linear acceleration. Now, I want to show you one more thing with linear acceleration, and that is a situation in which you have to solve for the time. I'm the one who wrote up the linear acceleration worksheet that's on Google Classroom. I'm the one who wrote the review sheet and the test for this chapter. When we get to that point, you will never have to solve for one of these up here, one of the speed values. You're either A, solve for linear acceleration, or B, solve for the time. So I'll show you how to solve for time here. Okay, so let's say that the acceleration is something like, just picking a random number here, let's say 7 miles per hour per second. And let's say that the final speed, you know what, let's use meters per second. We've done miles per hour already. So 7 meters per second squared. Let's say that the final speed is something like, I don't know, 21 meters per second, and the initial speed is, let's say, 15 meters per second. All right, we're going to figure out the time. So, what you do here, go ahead and simplify the numerator. I can see already this is going to be a pretty little number, so we're going to change this up to like 41, just to give us a little bit more, give us a little bit better result. So we go ahead and subtract here. 41 minus 15 is 26 over t, and that's going to equal 7. Now, what I have here, I'm going to move this up here so that it can be seen a little bit better. All right, so bring this up here, we have 7 equals 26 over t, and again the 26 is the difference between 41 and 15. So a couple ways to look at this. What I've seen with a lot of you, what you've done so far when you're having to solve for time or whatever happens to be in the denominator here of the fraction, is you just, some people say, oh, I just multiply. Well, okay, if you do 26 times 7, you get 182. You cannot tell me that 26 into 1 divided by 182 is going to be 7. All right, it doesn't work that way. So what we need to do instead is one of two ways. We can bring this t over like this. All right, so we have 7t equals 26, and then divide by 7. You can do it that way, or you can go like this, which might be easier for a lot of you, and that is to put this over 1 and then cross multiply and divide. Either method works. You still come up with the same answer. Some of us might be more inclined to see this proportion and say, oh yeah, I cross multiply and divide. So we can go ahead and do that. So 7t equals 26. 26 divided by 7t is going to be 3 point something. 3.71. All right, 3.71 seconds. Okay. So that's linear acceleration. Now I want to talk to you about angular acceleration. All right, angular acceleration looks like this. So angular acceleration, if you recall angular speed from last chapter, angular speed refers to how fast an object is rotating on its axis with respect to time. So for example, if we're talking about a wheel rotating on an axis as a car is driving down the road, we can look at angular speed and angular acceleration. So instead of looking at the entire car going down the road as far as acceleration is concerned, now we're just looking at, okay, we're going to step on the accelerator, aka gas pedal, and increase my speed. Well, during that process, how much faster is that wheel rotating on the axis? So that's angular acceleration. Now, I do want you to notice the similarities in the two formulas. And I'll identify the Greek letter here in just a second for you. Okay, we still have a difference of speeds, and we're still dividing by time. I'm going to rewrite that so it's a little bit more clear. I don't know how well you'll be able to see this. All right, so that's hopefully a little bit better for you. This is a Greek letter called alpha. Again, we use a Greek letter in our alphabet, or as part of science, because there's only 52 symbols that we have in our alphabet, and let's just say that there's a lot more quantities out there than that. I mean, some variables are used to distinguish or to describe more than one quantity, but we also use the Greek letters. And if you've been paying attention to the hurricane season this year, you know that the last named storm was Hurricane Delta, which is one of the, I think it's the 4th Greek letter if I'm not mistaken. Now, this letter here, it kind of looks like a W with some tails on it. This is what we call omega. That's the name of the letter. Just like we call this letter T in our alphabet, this is a Greek letter called omega. Again, this is called alpha. Now, alpha refers to the angular acceleration. it is measured in terms of radians per second squared. All right, recall a radian is another way to measure an angle, and we can easily convert back and forth between radians and degrees. 1 radian is 57.3 degrees. I would commit that conversion to your memory. This is omega sub f is final angular speed. Then you have omega sub I, which is initial angular speed. This is typed up a lot neater on Classroom and that compared to my sometimes not so good handwriting on the board. But you'll have that. And of course, t again equals time. So we can basically do the same kind of manipulations now with this formula, with angular acceleration formula, as we did with linear acceleration formula. So I'm going to go ahead and erase this. Give me some room here to work with some angular acceleration problems. So angular acceleration, for example, you might be talking about let's say the blades on a ceiling fan. Yeah, it's on the higher setting, and then it drops down to the lower setting. Okay, so what's that? What's the angular acceleration as that the speed of the blade changes? So we haven't done one with negative acceleration yet, so I'll show you that. I mean, it's still done the same way. It's always final minus initial. So let's say that the final angular speed is 1.8. Oops, it's radians per second, not meters per second. And let's say that it's up to 3.1, again, radians per second. All right, and that happens in a time of, I don't know, 5 seconds. So we go ahead and solve this. Again, figure out the difference and then divide by the time. So in this case, 1.8 minus 3.1 is negative 1.3. So we were at a higher speed of rotation, and then we reduced that rate of rotation. All right, and it happened in time of, let's say, 5 seconds. Again, just picking out a random number. So negative 1.3 divided by 5. Try it again here. Divided by 5 is 0.26. Remember, it's negative because we are slowing down. Your units here are radians per second squared. So these angular acceleration, linear acceleration, same type of formula, different variables, but you're still doing the same thing. You're finding that the difference between the final speed and the initial speed, and then dividing it by the time in order to figure out what your acceleration happens to be. If at any point you have questions about this, feel free to email me. And like I said, I'm more than happy to assist you. If we need to do small group work, I can come down to your labs. Just let me know.